there are basically several different ways we can classify what is an acid and what is a base. There's kind of three main theories behind this, and we want to discuss two in this class. But the simplest theory is called the Arrhenius theory, and it's named for a Swedish chemist, Svante Arrhenius. And the Arrhenius theory says that an acid is anything that once you put it into water, it breaks apart and it produces H+. So that's the Arrhenius acid. You put it into water, aqueous solution, it makes an H+. So for example, normally, for example, you would think HCl, that's two nonmetals. That's a covalent compound, molecular compound. So how does that make ions? Excuse me. But again, HCl is actually an acid. So when you put HCl into water, it actually does ionize, even though it's a molecular compound, which is weird. So you put it into water, and it does break apart into H+ and then chloride, Cl-. So therefore, that's considered to be an acid, because you put it into water, it makes H+. So we call that an acid. Now, however, we'll see, though, that H+ doesn't really last long in water. You do hear acid oftentimes called as H+, but really an H+, once it gets into water, H2O, it grabs onto that H2O and makes H3O+ really quickly, which we call hydronium ion. So that means then, in terms of that acid, H+, you will hear it kind of mentioned both ways. You may hear it called H+, or you may hear it called H3O+, which is the same thing. It's just an H+ with the water. So yes, you may hear both of those terms used interchangeably, H+ or H3O+. Okay? So I'm going to quickly run over that. Okay. And here's a picture, by the way. I got to speed up. This is actually a picture I was in Stockholm about a year and a half ago at the University of Stockholm. And this is their lab, which is named for that guy, Arrhenius Laboratory, you can see there. So that's the building name for him. And right over here to the left-hand side is a little statue of our buddy, Svante Arrhenius. If I can get it to come up here. There's a little picture, a statue of him right there. But yeah, he won the Nobel Prize. I think he was the second or third person to win, like 1903 or something, like real early on. He won the Nobel Prize, and as a thanks to him, actually for winning it, they actually built him his own house on campus, connected to his own lab. So it's very cool campus. So there on campus has like his own little villa, and then like a little not a tunnel, but like a covered walkway over to his own private lab they built him as a thanks there on campus. So yeah, it's kind of cool. Okay. Well, anyway, so like I said, acids, they are molecular compounds, but they actually do make ions, which is why they're unique acids. So when an acid goes into water, what's it make? It always makes H+, and then whatever else is left. So again, HCl, H+, and what's left? Cl-. So some kind of other anion. Okay? So you will always know it is an acid with a couple of things. When it's an acid, it's going to have AQ written after it, because it's only considered an acid when it's in water doing its thing. If it's by itself in the gas phase, or it's just pure and it's not in water, then it's not really an acid because it's not dissolving in water to make H+. So it'll have to be AQ. And you'll also notice the formula generally starts with H, the hydrogen. So like HCl, H2SO4, HNO3. So it'll start with an H, and it'll have aqueous at the end. That's your two big clues that you're dealing with an acid. So then H is the first thing in the formula, and it's aqueous. That's a clue you're dealing with an acid. Okay, so like I said, HCl, aqueous. H2SO4, aqueous. We'll see a lot of other ones as we go. Starts with an H, has aqueous. Starts with an H, has aqueous. Going to be an acid. Alrighty. So I'm going to talk about how do we name acids. So you are already pros. Hopefully by now you've only had like a month and a half to learn how to name ionic compounds and molecular compounds. And if you can name ionic compounds, you can name acids, because there's only 3 rules for naming acids, and they're based off the way we know how to name ions. So I'm going to write the 3 rules on here, as well as on the handout. The PowerPoint, but I also want to write them on here. So let me just make a new slide real quick. So here's a little handy chart. So it's based off whatever the H plus is partnered with. What's the anion that it's partnered with? If that anion ends in ide, so like chloride, bromide, what else can you think of ends in ide? Fluoride. Any other ides? Cyanide. Anything like ide, right? Then what do you do to turn that name into an acid? It's easy. So you just drop the ide, and you replace it with, you put a hydro on the front, and replace the ide with ic acid. So, HCl. Okay, if HCl makes an acid, it makes H plus and Cl minus. Cl minus is chlorine by itself, so chloride. So the acid, take off the chloride, chlor, hydrochloric acid. Just put the chlor in there. So that's the first rule. Question? No. Oh, okay. The next one is if the anion ends in 8. So what are some of the anions that end in 8? Phosphate, chlorate. What else can you think of? There's several. Sulfate. Think of any other ones? Carbonate, nitrate, all of these 8s. If it ends in 8, then you just take off the 8 and put on ic acid. No hydro now. So if the anion was, let's say, NO3 negative, nitrate, then the acid becomes nitric. Just take off the 8, put on ic acid. Pretty easy. And then the third one is ite. And we know ite typically happens when you had an 8 and you lost an oxygen, right? So like nitrite, sulfite, phosphite, right? Things like that. Those you do, you just take off the ite and put on us acid, O-U-S. Us acid. It's supposed to be an O, sorry. O-U-S acid. That's it. So again, it's really easy if you know how to name the ions. Because all you do is just take off that, replace it with that. Or take off that, replace it with that. Super easy. So let's go back and I'll show you a couple examples here. So, HCl. Okay, well, if that goes into water and it makes an H plus, then it must leave behind a Cl minus. Cl minus is called chloride. So the acid is hydrochloric. HBr. Oh, H plus must leave a Br minus. Bromine by itself we call bromide. So the acid is hydrobromic. See, so the brome stays, right? Just pull off the ide and put on hydroic acid. Even iodide, right? Iodide, iode. So take off the ide, hydroiodic acid. So that's all you do. So that's the first one. Okay? So have an example written down. HCl would be chloride going to hydrochloric. Okay, let's try another one. Let's try the 8s to X. Okay, HClO3 aqueous. That's an acid. How do I name it? Well, if that was an H plus, that would leave ClO3 minus. ClO3 minus, you know, is called chlorate. 8 to X. So chlorate becomes chloric acid. Chlorate goes to chloric acid. See how that works? Okay. How about H2SO4? Okay, well, H2. So now if I lose 2 H pluses, I'm going to leave behind SO4 2 negative. Because if I took off 2 positives, it would be 2 negatives. SO4 2 negative is called sulfate. Sulfate, right? Sulfate. Now you'll notice, though, the acid's not sulfic. We do put the back in there, sulfuric. So we only do that if the ion name has either a sulfur in it, then we don't make it sulf, we make it sulfur or whatever it was, or if it has a phosphorus in it, then we don't just call it phosphoric acid, we do put the back in there for those two. So, for example, let's say it was H3PO4. H3PO4. H3PO4 aqueous. Oh, okay. Well, if I lost 3 H pluses, the ion must be PO4 3 negative. That's called phosphate, right? Phosphate. Phosphate. Okay? 8 tells me go to ic. If I don't just make it, again, just make it phosphic, like you would normally, like I say with chlorate, you do put the back, so phosphoric acid. So I do keep the phos, but I put the or back in there, phosphoric acid. But again, that's if you have a sulfur compound or a phosphorus compound. That's the only two you got to put the little or back on the end. Okay, and the third rule was ite to us. So ClO3 is chlorate, so ClO2 is chlorite, so the acid is chlorus, ite to us. HNO2, NO3 is nitrate, so NO2 is nitrite, so the acid is nitrous. Just turn the ite to us. So that's it, just 3 simple rules, and you can name all these lovely acids. Assuming you know how to do the anions, which hopefully you do by now. Okay, so let's try a couple here. You have your handout there. If you do pull it out, got a bunch here to name. So let's think about this. Let's try the first couple together here. H2S. So H2S aqueous. Well, if I lost 2 H pluses, that must have left behind an S2 minus, right? How do I name S2 minus? How do I name S2 minus? Sulfide, right. Ide. Sulfur by itself. Oh, so ide tells me, yes, as Jen was saying, take off the ide and make it hydrosulfuric acid. So yeah, we'll put the back in there. So hydrosulfuric acid. Kind of made that a little messy there. I'm going to clean that up. So I tells me to do hydroic acid, right? Okay, how about the next one, HI? Okay, well, the H's come off as H pluses. So if that's an H plus, then the I must be an I minus. Well, how do I name this I minus by itself? What's that anion called? Iodide. Oh, look again. Ide. So what's the acid going to be? Hydro, it's hard to say, iodic. Hydro, and then ic. Hydro, and we keep the iode, and then ic acid. Hydroiodic acid. Okay? Let me do one more with you. HNO2. So, okay, so that came off as an H plus. That means this must be NO2 minus. How do I name NO2 minus? Nitrite. Because NO3 is nitrate. So, nitrite. Now, ite, not ide, ite. So what do you do with ite? Us. So the acid must be nitrous acid. Okie dokie. Okay, your turn. Try the next couple. Try HCN and H2SO3. Right. Again, it's all one word, not hydrocyanic, by the way. Hydrocyanic acid. Hydrocyanic acid. Okay, how about this one? H2SO3. Sulfurous, yeah. So I to us and put the back because it's sulfur. So sulfurous acid. Okay. Okay. It's really not too bad if you know the rules for the ions. Okay, let's try a couple the other way. So, chlorous acid. So that's the acid name. What's the formula going to be? Well, what does us acid tell me the ion must have come from? Ite. So, this must have come from, you're right, chlorite. What's chlorite's formula? ClO2 what? Negative. So if it's one negative, then how many H pluses do I need to balance it out? Just one. So it'd be HClO2, and don't forget aqueous. If it's not aqueous, we don't name it like an acid. Okay, phosphoric acid. Ic acid tells me it came from what? Phosphate. Ic acid to 8, so phosphate. What's phosphate's formula in charge? PO4, 3 negative. Okay. Well, now how many H pluses do I need to balance it out? Oh, if it's 3 negative, I need 3 H's. So H3 PO4, and don't forget the aqueous. Okay, your turn. Try the next 3. Hydrobromic, carbonic, and nitric. See, so HBr, hydrobromic, must be from bromide, so HBr, right? Because bromide is 1 negative, so I only need 1 hydrogen to balance it out. Carbonic acid. So ic acid came from 8, so carbonate. What's carbonate? CO3, 2 negative. So the acid must be H2CO3, aqueous. Don't forget the aqueous. Okay. Nitric acid must have come from nitrate. What's nitrate? NO3, 1 negative, so we only need 1 H, so HNO3 aqueous. Not bad, right? If you know the ions, it's not bad. If you know the ions, it might be a little bad. Okay, so that's the Arrhenius acids. How about the bases? Well, an acid, you put it into water, it makes H+. A base, you put it into water, and it makes hydroxide, OH-. So that's the definition for an Arrhenius base. If you put it into water, and it breaks apart, it makes OH-, then you got yourself a base according to the Arrhenius definition. Okay? Example, sodium hydroxide. We know sodium hydroxide is soluble. So yes, that goes into water. So it makes sodium ions and it makes hydroxide ions, right? Because you know sodium anything is soluble, right? So it's going to make sodium and hydroxides. Therefore, it is a base because it makes hydroxide when you put it into water. It makes hydroxide, that makes it a base. Okay, so, yeah, breaks it up, makes sodiums, makes hydroxides. Oh, hydroxides must be a base. Okay, now that is the basic Arrhenius theory there. Acids make H+, bases make hydroxide. That's kind of all there is to it on those, okay? Whoops, what is this here again? I have no idea. Okay, go back. Now that's the Arrhenius theory. Now there's also another theory called the Brønsted-Lowry. Now Brønsted-Lowry is actually a broader theory because a Brønsted-Lowry acid and base theory will encompass everything that falls under Arrhenius plus some other ones. So it's a little broader category. There's even a broader one called Lewis that encompasses even more, which we won't cover in this class, but come back in 110 we'll cover. But so Brønsted-Lowry is similar in that you put it into water, still dealing with H pluses, but now we call it an H plus donor. Now if you think about hydrogen, of course is number 1 on the periodic table, right? Which means it's got 1 proton, and when it's neutral, it's got 1 electron, right? Because they're always balanced out, positive and a negative. But But if it's H plus, that means it lost the negative. So all it has left is a proton. So an H plus is really just a proton, which is why you call it a proton donor. Again, it's all the same thing. H plus is just a proton. And then here's the difference then. Now a Brønsted-Lowry base is not something now with hydroxide, but something that accepts an H plus. So the acid gives the H plus, and the base takes the H plus. So that's the difference here between the Arrhenius. So now it has nothing to do with hydroxide. Again, this is a broader category because everything that was an Arrhenius acid is also a Brønsted-Lowry acid. Everything that was an Arrhenius base is also a Brønsted-Lowry base, plus other ones because it's bigger. Just a bigger category. Okay, well, let's look at how this might work. So here's a classic reaction you might want to write down. HCl, which we know is an acid, plus H2O makes hydronium and chloride ion. So, what happened in this one? Well, according to Brønsted-Lowry, if it's an acid, it means it donated an H plus to something, and whatever the base took the H plus. So if you look between the reactant side and the product side, the HCl gave the H plus to the H2O. So that left Cl minus, and that made this from H2O to H3O plus. So do you see how that H plus was donated? Let me draw a little arrow here, maybe that'll help. Oops. Right, this H went over here. See that? And so that lost the H, this gained the H and became hydronium. So yeah, one was an acid, gave a proton, one was a base, took a proton. Okay? Excuse me. Now how about the bases? Now the bases, like I said, the bases don't have to have hydroxide. An example one is NH3. So normally you say NH3, how's that a base? There's no hydroxide in there. You're right. But it does take an H plus now. So bases take an H plus. So in this case, if I was going to write it here with water, if this water gave an H plus over here, well then this becomes not NH3 but NH4 plus. You see that? If it gained an H plus, it went from 3 to 4 plus. And if H2O lost an H, it leaves behind OH. If it lost a plus, now it's negative. So you see, it did still indirectly make hydroxide, even though there wasn't hydroxide directly present in the NH3. It did it because it took an H from the H2O and it left HO, hydroxide. So, that's how it works. One is an acid because it gives an H plus, the other one's a base because it takes the H plus. It's on the receiving end. So, these are called conjugate acid-base pairs. So you notice, whatever was an acid, when it loses its H plus, like it became this, that is now a base. Because this one had an H plus to give, now whatever is left wants an H plus, makes it a base. This one was the base, so this one took an H plus, but now it has an H plus to give. It's an acid. So whatever was the acid became a base. Whatever was the base now became an acid. Let me say that again. You see here it has an H plus, so it's an acid. There it wants an H plus, so it's a base. You see that? So it was an acid, now it's a base. Here it's a base. Here it took an H plus, so now it has an H plus to give. So it was a base, now it has one to give, now it's an acid. So the acid becomes the conjugate base, the base becomes the conjugate acid. So you can always pick them out easy because they only differ by an H plus. So the difference in HF and F minus is only an H plus difference. The difference in H2O and H3O plus is only an H plus difference. So they only differ by an H plus, a proton. Okay. So let me show you one here. Let's try this one. So get out your hand out there. Let's look and do the first one together. Figure out what's the acid and what's its conjugate base and what's the base and what's its conjugate acid. So one of these is going to give an H plus, and one of these is going to take an H plus. So between HBr and H2O, which one is acting like the acid? Okay, the HBr is acting like the acid. So let me just write that here. This is acting like the acid. So, it's acting like an acid. It's giving an H plus to something. So after it gives an H plus, what did it leave behind? It left behind Br minus, right? So this must be its conjugate base. So these two you can see are linked together. This became that, right? Well, if the HBr gave the plus, then the H2O must have taken it. That makes it a base, right? Because you see between here and here, it gained an H plus, right? You see that? It was H2O, now it's H3O. Oh, it must have gained an H. So that makes it the conjugate acid. So the acid became the conjugate base, the base became the conjugate acid. So the one gave an H plus, now it's short one. The other one took an H plus, now it has an extra one. So it goes back and forth. Okay, questions on that first one? Okay, try the next one. What's the acid? What's the base? What's the conjugate acid? What's the conjugate base? So, which one of these two is the base? Which one is the acid? What's the acid? CH3NH2 or H2O? H2O is the acid. Okay, which means the other one must be the base. So if it's an acid, that means it gave an H plus. So what's its conjugate base? The OH minus, right? Conjugate base. Because again, they only differ by an H plus. And these two only differ by an H plus. So between NH2 and NH3 plus, it gained an H plus. So it must have been a base, which means this must be the conjugate acid. Okay? Okay. So let's look at this one. Let's say I told you HCO3 minus was going to act like an acid. What would its conjugate base be? So let's think about this. So if it acts like an acid, what's it do? It gives an H plus, right. So if it's going to lose an H plus, I'm going to put minus H plus here. What would it leave behind? What would its conjugate base be if it lost an H plus? CO3, 2 negative. Because it was already 1 negative, and now if it lost a plus, it must be another negative. So that would be the conjugate base. Okay, try HClO2. If that one lost an H plus, figure out what would it leave behind. Okay, so HClO2, if that lost an H plus, what would it leave behind? ClO2 negative. What's that called? Chlorite. Right. Okay, how about the other way? What's the conjugate acid if these are acting like bases? So if it acts like a base, what's it do? It accepts an H plus. It gains an H plus. So again, we're just going to gain one. We're not going all the way to neutral. So if this were to just gain an H plus. Oh, and then it would become HPO4. What would the charge be now? Now 2 negative. 3 negative and a positive makes 2 negative. Again, we're not going all the way to neutral. We're just saying just gains and H plus. Okay, and how about the next one? Right, if this gained an H plus, then it would become H2SO4. Right, good. Okay, so that's the conjugate acid-base pair. Now we discussed what are called strong electrolytes, weak electrolytes, non-electrolytes. We said strong meant you put it into water, 100% of it dissociated into ions. Weak meant much less than 100%. Same thing with a strong acid. A strong acid you put into water, 100% of it turns into H plus or hydronium. Example I already told you, HCl is not only an acid, but it's a strong acid because when you put HCl into water, none of it stays together. All of it breaks apart into acid and chloride, or hydronium and chloride. All of it. Okay? So it's 100%, so we have a single arrow. Notice we got a one-way street on that. We got a one-way arrow. Okay? Now the nice thing is, there are only 6 strong acids. So if you memorize these 6 strong acids, which I hope you will, then you know that every other of the thousands of acids in the universe have to be weak. There's only 6 that are strong. So if you know those 6, then every other acid you can think of, citric acid, acetic acid, scorbic acid, lactic acid, whatever else you can think of, it's got to be a weak acid. So, make a note of those 6. Those 6 are the 6 strong acids. HI, HBr, HClO4, HCl, H2SO4, and HNO3. So any other acid that you ever see means it doesn't dissociate 100%. Some of it stays together. It'll be a weak acid, as we'll see here in a second. Okay? Now, notice all of these acids have one H with them, except for sulfuric, right? Notice sulfuric is H2SO4. So all of the ones that only have one H plus or one proton, those we call monoprotic, one proton, because they only have one H. The one that has 2 H's, 2 protons, what do you think we call it? Not poly, I mean, it could be, but yeah, but specifically if it only has 2, di, yeah. 2 is diprotic. So H2SO4 though is diprotic because it has 2 protons, H2SO4, right? See, it has H2. So it has 2 protons. Okay, so yeah, so make a note to yourself, memorize those 6 strong acids, learn them, and then once you know those 6, you know every other acid, the thousands and thousands of them have to be weak. Okay, so strong acid, you put them into water, all of it breaks apart. None of it stays together. Weak is just the opposite. Weak, you put it into water, and now it's a little two-way street. Now we draw an equilibrium arrow. Because, yes, HF, you put it into water, some of it breaks apart, but some of that recombines and comes back together. In fact, most of it stays together. Only a very small percentage ionizes. Typically, you know, it's 5% or less. So 95% of it stays like this. Only a little tiny bit ionizes. So let's draw a little picture here. If I put HF in, see, like one of them broke up, but most of them stay together. So that's why it's a weak acid, because it doesn't 100% ionize. So that is, again, analogous to a weak electrolyte. Okay. Excuse me. Now notice here's our 6 strong acids again. So whenever that ionizes, the acid becomes the conjugate base, right? Well, it's a conjugate base because it can accept a proton now, right? Here it had a proton, now it wants a proton, right? Well, think about this. depending on the stronger the acid was, the better it was at giving an H plus away. The crappier, the weaker the base it is, the less it wants to take an H plus now. Because if this one really wants to get rid of an H plus, well then this probably doesn't want to take it back. Yeah.
Why is that one called perchloric acid?
Okay, ClO3 is chloric. If we add one, we discussed this in 100, but if you add an oxygen, we call it perchloric. So ClO3 is chlorate, ClO4 is called perchlorate. We didn't get into how to do the other oxygens. We don't do the one where you just have the oxygens, or you lose one was ite. But if you gain one, it's actually called perate. There's another one if you lose two, but we didn't do all those. But yeah. So if this is a strong acid and it really wants to lose an H plus, this is going to be a crappy base because it really doesn't want to take that H plus back. So that's kind of how it works. So the better the acid, the worse the conjugate base is, and vice versa. The worse the acid, the weaker the acid, the better the conjugate base must be. So here's a little chart, just kind of show you real quick. So these are getting better and better acids, which means their conjugate bases are getting weaker and weaker this way. But as they get to be weaker acids, they become better bases. So they just go opposite. Okay, I'm going to skip over that real quick. So, now notice, here's another diprotic acid. This is called, what's this one called? What's CO3 called? Carbonate, not hydro. Hydro if it's ide, just carbonic. Ate to ic, carbonic. Carbonate to carbonic. So, it has two to give, so it can actually do it twice. So we're going to do it in two steps. First it's going to lose one and make HCO3 negative. And then that's going to come along and do it again. And do it again and make another one. So it can give two protons. I can do it twice because it's diprotic. So it can actually do it twice. So here's the acid, here's its conjugate base. Or they can also act as an acid again and make another conjugate base. So we can do it twice. And again, let's say it was phosphoric acid, H3PO4. Well, we can have three reactions. We could lose H3 to make H2PO4, to make HPO4, just to make PO4. So we can do it 3 times. So yeah, you can just imagine it happening different times. Okay. I won't spend a whole lot of time on that. Go back to the PowerPoint if you need to review that a little bit here. Now H2SO4 I said is also a diprotic acid, but the difference is, I told you that was one of the 6 strong ones, right? So that means unlike carbonic, where it was a little two-way street both times, if it's a strong acid, it means what? 100%. So this can only break apart and make HSO4. So the first one's a strong one. But the second one is still weak. It's still a two-way street. But it is strong for that first one. So it is a one-way street for that first proton being donated. Okay, well again, you can come back to that. We need to get busting on here. How about bases? Same thing. Strong means 100% of it breaks apart into water. Weak means a tiny amount, 5%, 10%, 2% breaks apart. So NaOH, I already said, is a strong base. Put it into water, all of it breaks apart into sodium and hydroxide, sodium and hydroxide, sodium and hydroxide. All of it breaks apart. None of it stays together. That's why it's a strong base. Weak base. Well, I mentioned NH3 can be a base, ammonia, because you put it into water. Oh, real quick, by the way, there are 6 strong bases too. And they are the hydroxides of the group 1s and the group 2s, basically. So you see lithium hydroxide, sodium hydroxide, potassium hydroxide, and then the group 2 ones over there, some of these, calcium, strontium, calcium, and barium. Those 6 are the strong bases. So those, you put them into water, all of it breaks apart. None of it stays together. All of it ionizes. Okay? So I'll pause and write those 6 down. LiOH, NaOH, KOH, SrOH2, CaOH2, BaOH2. Those are the 6 strong bases. Okay. LiOH, NaOH, KOH, SrCa, and BaOH2. Got those? Okay, so those are the 6 ones. Now the weak ones, same thing. Put them into water, but now they don't 100%. Let me show you this picture. NH3, you put it in there. A few of them take the H+, right, do the acid, the base thing, but most of them don't. Most of them stay by themselves. So, again, it's not 100%. It's only a few of them ionize. Okay, so NH3. A couple of them make an NH4, take the H+. Most of them don't. So that's why it's weak, not strong. Okay, now, let's say this had a generic acid called HA for acid. I could write, so now I have an equilibrium reaction here, right? Well, we learned in the last chapter, we can write what's called an equilibrium expression, right, a K. So I can imagine writing a K, which is concentration of products over concentration of reactants. So I could write it and it'll look something like this. Concentration of hydronium times the anion over concentration of acid. How about the water? Don't include it, why not? Because we don't include solids or liquids. So it'll be something like this. So this K we call Ka, because it's for acids. It works the exact same way. So Ka. So this is a generic Kas. The hydronium or the proton times the anion over the acid. Ka. So we're going to spend some time on this. So let's discuss some of these. Okay, so let's look at how we could use this. So let's say, for example, we have formic acid. Formic acid is an acid found in ant bites and bee stings and things like that. I think actually like the Latin name for the ant is like something forminate or something, which is why it's formic acid. It comes from ants. Anyway, so here's formic acid. It's a weak acid. So, weak acid, so it donates an H+, makes H3O+, and leaves behind CHO2-. So I could write a Ka for that. Right? So, in my case, I could write it as, just back up here, and just write it the actual Ka. So in ours it would be, Ka would be, oops, wrong pin. Concentration of hydronium times CHO2 negative over HCHO2. Right? So that's how you write the Ka for that. Okay? Now, the value for that, if you were to measure the K for that, if you finish writing, I see several of you scribbling still. The value for that K is about 1.8 times 10 to the negative fourth. So, we learned if K is bigger or smaller, what does that tell you about the reaction? If K is bigger, what does that mean? More products and more reactants. If K is bigger, it means it must have more of this stuff, more of the products. If K is smaller, it must have more of this stuff, more of the reactants. So the bigger the K is, the more it's breaking apart, the stronger an acid is. The smaller the K, the more it's staying together, the weaker an acid it is. That makes sense? So the larger the Ka, the better an acid, the stronger an acid it is. The smaller the Ka, the weaker an acid it is. So here's a chart to show you a bunch. So this up here is the strongest on the chart, which even so is not real strong, but 10 to the negative third. Then all the way down, 10 to the negative fifth, 7th, 8th, 11th, 13th. So this one is stronger, right? Because this number is bigger, which means more of it actually breaks apart and donates H pluses. This, more of it stays together and doesn't give an H plus. Are you with me? So, okay, so you can kind of tell by the exponent there. Awesome. Okay, let's try to imagine writing a Ka expression for a couple of these. So let's say this first one acts like an acid. So I'm going to put it into water. Here, let's do it here. Plus water. So when I put it into water, if it acts like an acid, what's it going to make? What's it going to do? It's going to give an H plus to the water. So the water is going to become H3O plus, aqueous. And what will it leave behind if it loses an H plus? ClO negative, right? Oh. So my Ka expression must look like concentration of hydronium times concentration of ClO minus over concentration of HClO. Right? This product of reactants, again, don't include the water because we don't include liquids or solids, only aqueous and gases. Okay, why don't you try the next one? Try nitrous acid. What would that Ka look like? So imagine what it does in water. Write a reaction if that helps. And then what would it be? What are the products? What are the reactants? Okay, so you probably got something that looks like Ka equals concentration of hydronium times concentration of NO2 negative nitrite ion over concentration HNO2. And again, these could be switched. The order doesn't matter. It's NO2 and H3O plus doesn't matter. As long as it's the top's to the right and the bottom's to the right. But, okay, so that's just a way of determining, well, how strong is it really? You measure that Ka, the bigger the number is, the more it must be breaking apart. The smaller the number, the more it must be staying together. Okay. Now you notice in some of these cases, in that case, this reaction here that we wrote earlier, water took the H plus and acted like a base. And then I showed you one with ammonia where water gave the H plus and acted like an acid. So water did both. Sometimes it was an acid, sometimes it was a base. So when a substance can act like either an acid or a base, we call it amphoteric. Amphoteric. That means it can swing both ways. It can be an acid some days, it can be a base some days, whatever it wants to do. So sometimes it gives an H plus, sometimes it takes an H plus. Now, the kind of interesting thing about that is that means if you just have pure water, where you've got lots of waters in your pure water, some of your waters are acting like acids and they're giving up H pluses, and some of those waters are acting like bases, and they're taking H pluses. So even in pure water, you have this occurring. So we call this self-ionization. So all by itself, it's still ionizing. Where some of the waters are acting like an acid, and they're given an H plus to become OH minus, and some of them are taking an H plus to become hydronium. So right now in your water at your house or in your bottle, if you have some water handy, do you have actually little bits of acid in there and little bits of base in there? It's not really just H2O. You have some hydronium and some hydroxide in there because it's amphoteric. Now it's not much though. Not much of it actually forms hydronium and hydroxide. It's only very little concentrations. So I'll give you a number here once I see you're done writing. Okay. Now the actual concentration is only a little. If you were to measure, well, how much of hydronium and hydroxide was made, it's only about 1 times 10 to the negative 7th. So not much of it. So 0.0000001 molar. So not much of it actually does it. But there is some that does it. So let me go back over to this other equation. So that means these concentrations here, right? This concentration is about 1 times 10 to the negative 7th, and this concentration is about 1 times 10 to the negative 7th. So if I was going to write a K, let's imagine I wanted to write a K for this. Well, it would be concentration of hydronium times hydroxide over, 2 waters are both liquid, so over nothing, right? So it'd just be concentration of hydronium times concentration of hydroxide. So we give this K a special name. We call it the KW for water. And if the hydronium is 1 times 10 to the negative 7th, we said, and the hydroxide is 1 times 10 to the negative 7th. It's a little messy, sorry. That means the KW must be 1.0 times 10 to the negative 14th. So this right here, let me get a different color here. So this right here is the KW for water. So the amount of acid times base, hydronium times hydroxide, in water is always 1.0 times 10 to the negative 14th. 1.0 times 10 to the negative 14th. Let me go here and I'll show you it again. I have it over here too. So that's interesting because that means anytime you have a solution in water, which most solutions are, like your body's in water, right? Or anything in the lab is pretty much in water. Anytime you have any solution in water, the amount of the acid times the amount of the base is constant. It's always 1 times 10 to the negative 14. So that means I have a solution and I begin to add in some water, add in some acid, and the hydronium goes up, 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 up. In order for that to stay constant, it means the hydroxide must be going down, 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 down. Because if both went up, it wouldn't be 1 times 10 to the negative 14th anymore. That would get bigger too. But if that has to stay constant, if the acid goes up, the base must go down, and vice versa. If the base goes up, the acid must go down. So in water, that's a very important thing to note. So hopefully you have that written down, highlighted, star something. Because if you know the hydronium, well, the hydronium times the hydroxide has to be 1 times 10 to the negative 14. So if you know the hydronium, you can find the hydroxide. If you know the hydroxide, you can find the hydronium. One goes up, the other goes down, and vice versa. They always just go inverse. So if it gets more acidic, it must get less basic. If it gets more basic, it must get less acidic, in other words. Okay, let me show you how this works. So, let's just get this good. I told you all this. Because we're awesome. Okay, let's say we have, it says, what is the hydronium concentration if the hydroxide is 5.0 times 10 to the negative 9th? What is the hydronium concentration? Well, I just told you that the hydronium times the hydroxide is always 1.0 times 10 to the negative 14th. Well, if the hydroxide is 5.0 times 10 to the negative 9th, I can find the hydronium, right? The hydronium then must be 1.0 times 10 to the negative 14th divided by the hydroxide, right? Which in our case is 5.0 times 10 to the negative 9th. So, get out your calculator. Let's try our old friend, the exponent key. 1 exponent negative 14 divided by 5 exponent negative 9. See what you get. Don't forget, please use the exponent key. Don't try to do times 10 to the, you will get some crazy answers. So what's the concentration of the hydronium? Yep. And it's constant, so it's going to be molarity. Molar, because it's concentration. So yeah, so this relationship right here, like I said, very handy. The hydronium times the hydroxide is always 1 times negative 14. Yeah, I would give you that on a test or a quiz, but you just got to know how to use it. So if you know the one, you can find the other. Okay, a couple minutes here. Let's try one more. How about this one? Lemon juice, if the hydronium is 2.0 times 10 to the negative 3rd molar, what's the hydroxide concentration? So try it out. See what you get. Okay, that sounds reasonable. Whoops. Let's do it real quick. So that means the hydroxide concentration must be 1.0 times 10 to the negative 14th divided by the hydronium. So 2.0 times 10 to the negative 3rd. So 5.0, 2 sig figs, times 10 to the negative 12. Molar, because again it's a concentration. Molar. Okay, I think we're out of time. So I'll see you in about 10 minutes. Like I said, in labs. So we'll go ahead and turn your pre-labs and everything first. And we'll lecture a little bit, see how far we can get, and then we'll do whatever lab we have time for. And then we'll discuss the lab exam a little bit to you. Okay, see you in 10.